Hello everyone, and today I'm going to show you how to solve the problem's number of provinces. So there are n cities, some of them are connected, while some are not. So if city A is connected directly with city B, and city B is connected directly with city C, then city A is connected indirectly with city C. A province is a group of directly or indirectly connected cities, and no other cities outside of the group. So, for example, here in this one, you have two provinces actually, because you have two cities that are connected to each other that consists of one province, and three is basically another province. Three isn't connected to anything. In example two, we have three provinces that aren't connected to each other. So, if as you notice here, you have an adjacency matrix as an input. If you may think what's happening, like why is there a 1 at the first, why is there one at the middle, and why is there one at the end? It's because each of these cities are connected to themselves. And it also makes it easier to use union find, which is basically a data structure we're going to be discussing. I'm splitting this into two parts. The first where I actually discuss about the union find, and then the other part I am going into how to solve this problem using the union find. So let's get into the union find. So what is a union find? So a union find is a data structure that maintains a collection of what's called disjoint sets. Here's an example of two disjoint sets. Let's say A is 1, 2, 4, and B is 3, 5. These two are sets. And how do we know if they're disjoint? It's because when we merge them, or whenever we take the union of these, we get all these elements. So 1, 2, 3, 4, 5. So you can immediately notice that the cardinality of A is 3, and the cardinality of B is 2. So two disjoint sets will have cardinality of A plus cardinality of B. So the cardinality of A union B is going to be equivalent to the cardinality of A plus the cardinality of B. If the two sets aren't disjoint, we also have to subtract the cardinality of the intersection. So that will be A intersects B. However, we know that the intersection of two disjoint sets are empty. So this is not considered here. So if the two sets are disjoint, we're only going to be considering this part. So yeah, that's pretty much how you understand the disjoint sets in particular. How do we actually use these disjoint sets in practice? We're going to implement some sort of data structure like union find here. So how do we keep track of all these disjoint sets? So typically we'll be given like some elements here, and we would want to store them each in a disjoint set. And that's what we'll typically do in this purpose. Here, let's say we have 8 elements. So this is how we're actually going to keep track of the sets. There is going to be another array that we'll need to keep track of, and that is the size. There is another method called union find by rank, but getting the height of a tree is kind of a more advanced process. Even though it is more optimal, I am going to just discuss the union find by size. So this right here is the parent. It's okay if you don't know what this is. And then of course we have an array with the same number of elements. This is very important. You want to make sure that you have the elements here. So we have the sizes. Okay, so we're just going to say parent and then we have size. So as you see, you can recall how many disjoint sets do we have right now? So we have 3. Now, how do we get here? Yeah, so size is going to be of set A. We're going to have 4. And we have other implementations, of course. We have 1, but as you see, others can have like 4, 4, 4. But then we will set that to 0, and then 0. And then we also set F to 0. And then we have D, E, and G. So D has 3 elements, so 3 will go into size. E is not a representative, so we will not consider this. And G is not a representative, so we will not have a size. And H is going to be 1. So the number of essentially representatives are going to be a number of disjoint sets that we're going to have. and this is useful for helping us find the unconnected components, and will also help us for finding the number of provinces in our LeetCode problem going forward. So, okay, so let's sort of apply a find operation first. So, find. Find will basically refer to what is the meta parent of each, what is the parent of any representative. So, if a node is very deep in a tree, then we want to get its highest representative. So F's representative is C, and C's representative is A. So therefore, the representative of F is going to be A. So even down the depth as we go, the representative will still be this. But we also, oh, I forgot about the parents. So A's parent is going to be 0, B's parent is going to be 0, or A, C's parent is going to be 0, and then D's parent is going to be 3, basically itself, E itself, F is going to be C. Now, it's going to be easier to actually do FC, so it's the second index, because every time you go to the second index, every time, you're going to be going to the index of this element. So index 2 will be somewhere here, and then 0. Index 0 will be here. And so how do we know when we have reached a representative? So we reach a representative if we reach that index and the value matches. So this is how we know we have some sort of representative. And similarly, we can also do G and H, so 3, and then we also have 7. So therefore, these are all the parents. We can keep track of them. So now this is going to be it. Let's try some find operation. So find F is going to be, okay, 0. Find C is going to be 0. Find B 0. Find A 0. And then find D is 3. Then we have find E is going to be 3 because we go up. And then find G because we go up to the representative, which is 3. H is basically itself's parent, so 7. We're going to do the harder part. It's actually the unioning. It's actually going to be unioning these disjoint sets. So if we wanted to union something, we can union like anything. It doesn't have to be the representative necessarily. So then if we wanted to consist of this, we need to first of all check about the size. This is where the size comes useful. We have 3 cases. Okay, the cardinality of set 1 is greater than the cardinality of set 2. These are for any arbitrary sets. This is case 1. Case 2, we have, okay. Case 2, we have that the cardinalities are equal. And case 3, we have the cardinality of the first is less than the cardinality of the second. I will be doing all 3 cases in code, so it'll be much more clearer. Anyway, let's get to it. If this is a case 1, so the cardinality of this set, F, is basically going to be, the size of F is going to be, if we use a find, then this is going to be, we have to basically calculate the size of find F. So that would be 4. So then, so that'll be 4. So 4 is definitely greater than 1. So we ran into case 1. So if this is a case 1, we make the parent of H the parent of first set. So we will basically add H as a child of A. And then we also got to make sure that we remove it as a disjoint set. So this is going to be it. Now, how does this impact the array? So A will have H as well. So H's parent is no longer 7. It's going to be 0. And we also do not have the disjoint set of H anymore. So therefore, this is going to be 0. Okay, so we also ran into a case 1. If they're equal, pretty much do the same thing. Now, what if, and then if this is a case 3, then you will make second, you'll make the first set a child. Let's say there is an I and J. So I and J here. Okay, and let's add an I right here and a J right here. J's parent will be D, so that'll be 3. and highest parent is going to be G, so that's 7. All right, and then we'll also have to update these accordingly. Let's also add K. So K right here, K will be 3, and this should represent K as well, so that'll be 3, this set here. Now this is where we have something here. We have a case 3, so we can add A as, okay, we can add D as the representative of A. A is no longer the representative. We set A's parent to D. So that would mean, if anything, A's parent will, instead of being 0, it'll be 3. And what does this mean for the size? For the size, it means that A is no longer the representative, so this will be 0. And the size, this was not supposed to be 3, but this size would actually be, okay, the number of nodes here. So notice here we have 11. We just added 3 more, so I, J, and K. So that is basically how a union operation works. And now let's actually apply it to the code. Say this right here is a graph, and then we have 1, 2, and then we have 3. This has 2 connected components, but we are trying to find it. So we can use our adjacency matrix. We have 1, 1, 0, and then 1, 0, 0, and then 0, 0, 1. That's right. So first of all, we have to write the graph in terms of its edges because by our union, edges are going to be the best way. First of all, traverse through this matrix here. So 1, 1 is going to be an edge, and then 1, 2, 2, 1, and then we have, wait, 3, 3 actually. So these are all the edges. The best way to store all these edges is in a list. So essentially you'll be having a list of lists. So after this, what you want to do is make 2 arrays, one for the parent and another for the size. So this is going to be 1, 2, 3. Usually use actually this is kind of supposed to be one index below, but I'm just saying that this is 1, 1, 1, 2, 2, 1, 2, 2, 3, 3. These are technically all the edges. I'm just following along, but indices start with 0. So we're just going to go ahead and start off this. So we will have 3 disjoint sets to begin with. So we'll have 1, 2, and 3. And assuming they have a loop to itself. So this is P and this is S. P is for parent and S is for size. So the parent of 1 is 1. If you were to implicitly use some sort of hash map to convert this to an index, so this would be 0, this will be 1, and this will be 2. We still have 3 disjoint sets, so each of the sizes is going to be 1 because each disjoint set has 1 element. Here's the thing though, what are we doing now? So we'll be applying the union operation to all these edges. So here's how the union is actually going to work in this case. We will have to retrieve the values when we apply find to the start and the ending. And the main reason is that we want to check to see if the component is the same. 1, 1, so 1 is equivalent to 1. Find 1 is the same as find 1. It's the same as itself, basically. We can go into our next edge, so 1 and 2. 1 and 2 had different parents, so if we apply find on both numbers, then we'll basically have find 0 and find 1, because we do not know, like, the names of, like, the cities or something. 1, 2, and 3, so we can actually union this and this is so we don't have any complications here. So 1, 2, and this will no longer have a loop. So that means we can update 2's parent to be 1. In other words, index 0. And here we'll have size 2. The second disjoint set is no more, so that will be 0, and then we'll have 2. And then we will apply to 1. Now notice here that find 2 is the same as find 1. Because the parent of 2 is 1, and the parent of 1 is also 1. So we're skipping this edge. Same for 2, 2. And how about 3, 3? So 3, 3, we cannot do any unions. So obviously we are done. So the final thing to do to count the number of provinces is to sort of traverse through the array and count all the non-zero values. In this case, we have 2 non-zero values. There is going to be no case where it's going to be all zeros. So this is one thing to make clear. So therefore, we have 2 connected components or number of provinces. So let's actually go ahead and do the code. Let's actually convert this adjacency matrix to some edges here. So we're going to go ahead and traverse through the matrix. Okay, so for R in range, to get the length of the adjacency matrix, so len is connected. And then for C in range, len is connected. Now, notice here that we have our assumption that adjacency matrices are always going to be square, so we can let this one slide. We can have len is connected. So then comes actually importing the edges. Okay, silly me, I forgot to say where to store them. Okay, so edges and then edges dot append. So we're going to append, let's say, a list containing R and C. And then that's going to be it for the edges. Let's go ahead and define the union and find here. So, okay, first of all, we need a parent and size. So parent is going to be, we're going to be using, it'll be I for I in range. And then to get the number of, the length of the adjacency matrix is basically a number of vertices in the graph. So we can apply len is connected. So that's for the parent. The size, on the other hand, is going to be 1 because initially we're going to have n disjoint sets. So we're going to have the list of 1 times the length of this thing here. So this is going to be the number of disjoint sets. So obviously we don't need this x in parentheses. And now we can obviously apply the union and find method. So define, find. Let's do find first. So we have city and we need a parent. So recall that in our demonstration, to find like a representative of a city, like a meta representative, we are going to go ahead and refer to the parent array, city. However, we want to keep cycling until get a representative of itself. So while we got parent at index city is not equal to city. Okay, after this while loop, so while we have parent, okay, city is going to be equivalent to parent city. So what essentially that will do is set the current city to whatever's in that particular index of the array. So if the parent of 4 is 2, the new city will go to 2. And then 2's parent is 0. The new city will be 0. And this loop will terminate when the city is going to be the city. So obviously we have to go ahead and return city. So return is necessary because we are going to be using it in union. And speaking about union, we will actually take in 2 cities. So city 1, city 2, and then we have parent set, and then we also have the size set. So right now we're taking in the size because it is much cleaner. Let's go ahead with this union here. First of all, we have to go ahead and find all the cities. So find the representatives of city 1 and city 2. So let's do find 1 and find 2. So that'll be equivalent to find city 1 and find, whoops, and outside the parentheses and find city 2. So yeah, there we go. Let's go ahead and actually, if 2 elements are in the same sets, there is no point of unioning these sets. So essentially we're going to do nothing. So if find 1 is not equal to find 2, this is what we're going to do. We have our 3 cases. So our first case is if the size of city 1, find 1, because city 1 is obviously going to set it to 0. If the size of the first is less than the size of the second of find 2, then what we're going to do is set the representative of the first to the representative of the second. How do we do that? So parent, parent find 1, that'll be equivalent to find 2. Else, we can pretty much do either. In the else case, then we're going to be doing parent find 2 is equivalent to find 1. So yeah, that's pretty much it for the find. So the main reason we're including this equal within this if is because we can leave it out, but essentially in equal, we can either set the representative of 1 to 2 to like the representative of the second, or we can set the second to the first, and pretty much you'll achieve the same thing. So that is pretty much it for the union operation. Now, how are these actually used here? Now, we're not actually going to be using the find here, but we only use the find for the union. So this essentially is the union find method. But after we define this union thing, we want to go ahead and actually traverse through all the edges. We want to basically union all this here. So city 1 is basically edge 0, and we also have edge 1. And this is entirely legal because each list inside element edges will have 2 elements. So obviously union this, and we also have to take in the parent and size as there. Oh, also we have to, and also a very, very typical mistake, you also have to change the size of that particular thing to 0. So parent of find1 is equivalent to find2. So therefore, the size of find1 is no longer existent, and therefore here, size of find2 is no longer existent as well. So 0, that'll be 0. So we basically union these. After we're done making the disjoint sets, we will initialize to the size. So size, or s in size, if s is not equal to 0, this is an easy logic to check something is not equal to 0. If s is not equal to 0, we also have to keep track of num provinces. So num provinces is 0. So we will increment the number of provinces if the given size is going to be 0. So this is plus equals 1, and then we're going to essentially return the number of provinces. Okay, I forgot a parameter here. I also forgot to update the size of find1, of find2 actually. So we also have to increment the size of find2. And for the else clause, we also have to increment the size of find1. That's what I forgot to do. So if okay, is connected RC is equivalent to 1. There we go. Got this. And also we should submit it to see if it's accurate. So there we go. We got it. So thank you guys so much for watching. If you guys enjoyed, make sure to leave a like and subscribe. Of course, we're going to see you guys in another video. Peace.